everyone. In today's session, we are going to cover the basics, the extreme basics of the airfoil theory, and we'll be answering three big questions, namely what, why, and how. What are airfoils? Why are airfoils used? And how do airfoils function? These are the three motives of today's lecture. So today's session is it forms the very fundamentals of aeronautical aerospace engineering, and it is like very basic. If I were to say, then I would say that the airfoil theory is the A behind aerospace engineering. So it's very important and very important. Yeah, that is it. So without further delay, let us begin. This is the general flow of the presentation. Firstly, we'll start off by answering what are airfoils. Why, then we'll go on to why are airfoils used. First, if we understand what is an airfoil, then we'll be able to answer why are airfoils used. Then after why, we'll explain how do airfoils function, and then I'll give some extremely important features of the airfoils, like the chord line, angle of attack, etc. etc. So yes, let us start from what are airfoils. So, what is an airfoil? If someone asks you that what is an airfoil, you'll answer by saying that an airfoil is a curved 2D shape which is designed to deflect oncoming air into a specific direction to produce an upthrust force known as lift force. Now, okay, this is a very bookish definition and not many of you might understand. So, like, for example, there is a square, and when you extrude a square, you get a cube or a cuboid. Okay, where there is a circle, when you extrude a circle, you get a cylinder. In a similar way, when you extrude an airfoil, you get an wing. You get a wing, an aircraft wing. So, when you keep that, like when you keep that wing and shoot air at it, okay, or when you keep that wing and shoot air at it, the air will get deflected downwards. Now the air will get deflected downwards. Now, due to equal and opposite reaction, the airfoil will get pushed upwards. Now this pushed upward, the force that will push it upward is known as lift force. Okay, so yeah, so an airfoil deflects the wind downwards so that the equal and opposite reaction causes the airfoil to go upwards. So this is what is known as lift. So you can say that an airfoil is a 2D shape which generates lift. An airfoil is a curved shape which generates lift when placed in a fluid flow. Now, these are some famous airfoil profiles. These are all early airfoil profiles, like which were discovered or which were drafted in very a long time back, as you can see here. And these are some common subsonic airfoil profiles, which means they are used in the subsonic regime. And here, like as you can see here, the Clark Y is a very famous airfoil, and it is used immensely in the RC aircraft model aircraft domain. So now answer why are airfoils used. So before understanding the why, you must know that the about the four fundamental aerodynamic forces. So there are four fundamental aerodynamic forces that act on every flying body. Let us consider a plane in this case. So there is weight. Weight is essentially gravity or the pulling down force that Earth exerts on the body. So weight or gravity is simple. There is thrust. So thrust is generated by any sort of force. Like you can take air turbine engines, you can take propellers, you can if you even throw a paper airplane by hand, that is also thrust. So thrust acts in the direction of the flight. Okay, thrust acts in the direction of the flight. In the opposite of the direction of the flight acts a force named as drag, which is due to the uh, air resistance that occurs due to the aircraft body. So thrust acts in the direction of the body, weight acts downwards, and drag acts opposite to the direction of the body. So you may wonder that an aircraft goes up. So there must be a force that causes the aircraft to go up. And yes, that force is named as lift. So how is lift generated, you might wonder. So the sole purpose of the airfoils is to generate the lift force. You can generate thrust by engines. Drag will be present because of the air resistance. Weight is always present. So the force that causes the aircraft to go upwards in the air, then the force that causes the aircraft to fly is known as lift force. And airfoils generate this lift force. So now you may wonder, how do airfoils generate lift? So there are two common theories, like two famous theories that explain the lift generation by an airfoil. One is the Bernoulli's principle. Second is the Newton's second law. I personally find the Bernoulli's principle to be more convincing and simpler to understand. So in this session, I'll be only explaining the lift generation by the Bernoulli's principle. So before explaining how Bernoulli's principle defines airfoil, let us first understand the very basic statement of the Bernoulli's principle. This is not actually the scientific statement, but rather an inference of the Bernoulli's principle, which is that higher velocity leads to lower pressure, and lower velocity leads to higher pressure. Now you can prove this mathematically, and I have done it in the very first session of Quanta effect. If anyone wants to see, then he or she may see the recording of it. Okay, so we know that according to the Bernoulli's principle, higher velocity of air leads to lower pressure region, and a lower velocity of the air leads to higher pressure of the higher pressure region. Okay, so an airfoil is curved and it is shaped in such a way that the air on the top of the surface, on the top surface or the upper surface, moves faster. Okay, it has a higher velocity compared to the air moving downwards, like on the lower surface. So ultimately, the higher velocity on the upper surface causes a low pressure region to be formed above the upper surface, and a high pressure, the lower velocity and the lower surface of the wing causes a high pressure region to be formed under the wing. So due to the pressure difference, here pressure is high, here pressure is low. Naturally, the wing would be pushed upwards. Now this pushed upwards is the lift force. So this lift force arises due to the pressure difference or between the lower surface and the upper surface. We can also state it mathematically. So this is the general expression of the Bernoulli's theorem. I will not account for the difference in height in this case. Okay, I am not going to account for the difference in height. So ignoring the difference in height, we get this, that is static pressure plus half rho is the density of the medium, in this case air, and v is the velocity of the fluid flow. It's always constant. So since it's always constant, the lower velocity and the higher pressure would be equal to the velocity and the lower pressure when added, like in this format. So this is the PU here is the static pressure on the upper surface, and VU here is the velocity at the upper surface. Similarly, PL here is the static pressure on the lower surface, and VL here is the velocity at the lower surface. So this from this expression, as I mentioned, that the lift force is generated by the pressure difference. So this means we need to find the pressure difference. So transferring this term here and this term here and taking half rho common, we get this expression. And PL minus PU is delta P, or the pressure difference. Or okay, so pressure difference. Yeah. Now you may know that pressure is force upon area. Okay, force per unit area is known as pressure. Now we need to find out the lift force. So force would be pressure times area. So area times the change in pressure or the pressure difference, we will get that will give us the lift force generated by an aircraft wing or an airfoil. And A here is the surface area of the airfoil. So that is it. Okay. So that is how an airfoil or an aircraft wing or an airfoil generates lift. Now, here are some basic features that are extremely helpful when studying aeronautical engineering. And these are some basics about airfoils. Now, first term is the chord line of an airfoil. So, a chord line is an imaginary line that is drawn in the direction normal to the airflow, and it connects the leading edge to the trailing edge. Now you may wonder what is a leading edge and what is a trailing edge. It's very simple. Leading edge is the point that faces the airflow. Like it's like here, and the airflow would be like this. So this would be leading edge, and the trailing edge is the end of the airfoil. So it is quite it's quite understanding. You can understand it by the words itself. Leading means the part that will lead the airfoil, and the trailing means that would be at the trailing point. So that is it. The chord line joins this. However, the chord line is always normal to the airflow. This is the direction of the airflow, and this is the airfoil. So yeah, this is uh, a note that you must remember, that chord line is normal in the direction of the normal airflow, and it also joins the leading edge and trailing edge, and it is a straight line. Now let us come to angle of attack. Angle of attack, or AOA or alpha, whatever, is the angle between the chord line of an airfoil and the airflow vector, or the direction of the relative wind and the angle between the direction of the wind and the chord line gives you the angle of attack. So, you could, in simple words, in layman terms, you could say it as the tilt of an aircraft wing or an airfoil. Okay. So that is that. Now, AOA is extremely important when it comes to lift generation. Every airfoil has its critical angle of attack. You increase the angle of attack, there would be increment in the lift only to a certain extent. And after that certain extent is passed, there would be a flow separation, and that is known as stall. More about that we will talk in the future sessions. Now, this is the mean camber line. Okay, so what is the mean camber line? Mean camber line is an imaginary line that join. Keep a note that this curved is only in the case of asymmetric airfoils. In symmetric airfoils, mean camber line is straight. Okay, yeah. So getting back, an imaginary line that joins the leading edge and trailing edge is, and is equidistant on all points from the upper and the lower curved surfaces, and it basically affects the curvature of the airfoil. So in an airfoil, uh, we have to draw a line that joins this leading edge and this trailing edge. And the distance at all the points from the upper surface and the lower surface would be equal. So as you can see here, this purple line is equidistant from this point, 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 this point. This distance is equal to this distance. This distance is equal to this distance, and so on at all the points. And you could also understand it by circles. If you draw a lot of circles with the upper surface and lower surfaces being tangential, the center of the circle, after joining the center of the circles with a curve, you will get to the camber line. So yeah, this is how you define the camber line, or more precisely mean camber line, because yeah, mean camber line. Now let us understand what is camber. Camber is the basic measurement, sort of, you can say it's the basic measurement of the curvature of an airfoil profile. Geometrically, you can think of camber as the maximum distance between the chord line and the mean camber line. So this is the chord line. As you can see here, chord line is straight. In this case, it's not a symmetric airfoil. So in this case, the chord line is straight. Okay. And now we note that the chord line need not to be at equal distances from the upper surfaces and lower surfaces. Okay, it does not have to be equal distance. Like this distance is greater than this distance, but still this is the chord line, right? The condition for mean camber line, that it has to be, equal distance from the upper surface and the lower surface. So this is the mean camber line, and this is the chord line. When you plot these two, the maximum distance between these two will be your camber. It directly affects how much curved, or how much curved your airfoil is, or what is the curvature of the airfoil. No, so this was it for today's session. If you have understood today's session, it will really help you with the future topics that would be the Cartesian representation of airfoils, like how to plot the airfoils on a graph for better study, the coordinates and all, the NACA airfoil nomenclature system. So there are a lot of airfoil profiles in existence. There is a nomenclature known as the NACA and NACA nomenclature. So this basically tells you numbers of the airfoils. Okay, so it is basically how you name an airfoil. So I will talk about it. Then different types of airfoils, like the airfoils of the subsonic regime, transonic regime, supersonic regime, symmetric airfoils, asymmetric airfoils, etc., etc. Coefficients of lift, drag, and moment. So these are properties or features of an airfoil, and it shows you how aerodynamically efficient an airfoil profile is, and yeah, so basically how they affect airfoil efficiency. And after all these, we'll be ready for understanding what are wings. Okay, wings, how to create your wing, what are the different types of wing, how do different types of wings are used in for different purposes, and etc. etc. So thank you all for listening patiently. Hope you understood everything. Thank you. Signing off.